So this morning we have a tutorial by Bella Fair. You guys all know Bella. He graduated from Cornell in 1974, where he worked, until 1987, where he went to Utah State University, not University of Utah. That's right. Utah State University. And this morning, he's going to talk to us about the equatorial ionosphere. All right, let's welcome Bella.
Thank you very much. Actually, it's a pleasure to make this presentation here, where John Sarr has been for a number of years, and John Sarr, for those which go back a few years, will know that John Sarr also came from Cornell, and actually John and I did a lot of joint work together. What I'll do today is give you a general idea of the very broad range of topics which can be studied in the equatorial ionosphere. I was asked to make this a fairly basic, and certainly will be a basic one. So so this is basically the outline of my presentation. I'll start with the Earth's magnetic field, which plays a fundamental role in determining a lot of morphology, especially in terms of longitudinal variation in the equatorial ionosphere, introduce some of the unique phenomena in the equatorial ionosphere, and focus heavily on transport processes which affect these unique phenomena, brief description of measurement technique, and deal with electrodynamic processes. And I'll highlight some of the challenges which we face in making further progress in this field. So the Earth's equatorial ionosphere is host of one of the most complex phenomena in the upper atmosphere. I want to convince you that this is really the case. Actually, a lot of work has been done in identifying basic signatures of, say, solar tides, lunar tides, planetary waves, gravity waves, El Niño, earthquakes, tsunamis, lightning, and high-latitude stratospheric warming. So all these processes have signatures in the equatorial ionosphere. Some of them are not fully understood or characterized, but we know that at least this number of processes are important. So, and these are under quiet conditions. So under disturbed conditions, you have essentially everything which happens in the solar wind and in the magnetosphere is reflected in transport processes at low latitudes. Coronal mass ejection, co-rotating interaction region, substorm, solar wind variation, dynamic pressure changes, magnetic reconfiguration, solar flares, and Joule heating. So the bottom line, in the normal circumstances, all these processes could be affecting the equatorial ionosphere. This is essentially our challenge, how to peel off each one of these and try to understand them better. So what makes life a little more interesting and challenging, of course, is the fact that all these processes affect the equatorial ionosphere in a local time, seasonal, solar cycle, longitude, magnetic activity dependence. And actually, even though the equatorial ionosphere seems to be a restricted region, actually you have to understand it. What happens in the equatorial ionosphere affects 30% of the globe. So I'll focus on some of the main properties of the equatorial ionosphere, which you have been studying, and especially focus on electrodynamic processes. I'll focus essentially on processes. A lot of very nice simulation studies, theoretical studies have been done, but of course, I do not have time to cover them. So this is essentially the Earth's representation of the Earth's magnetic field. And what is fundamentally important here, there's a lot of variation of the Earth's magnetic field as a function of longitude, and also in terms of intensity. Magnetic field is strongest over India and weakest over South American region. And particularly one is very fundamental is this change in the slope of the magnetic field lines in the American sector, which makes the study of this sector by far the most complex from anywhere in the world. In addition, what's happening in the equatorial ionosphere, the magnetic over South America, is that the magnetic field is undergoing a very fast secular change. My Brazilian friend measured the variation of the magnetic equator in tens of kilometers per year. So initially the Brazilian equatorial station, when I started work, this was the magnetic equator. My friends from INPE put a radar here, but that radar cannot measure spread F very well because the magnetic equator here, it's around here already. So essentially it's a race against time. And what makes difficult is to study essentially secular variations, because we don't know essentially why these are due to changes in the upper ionosphere as a whole or simply reflect changes in the magnetic field. The other fundamentally important feature of this variation is the fact that one fundamentally important quantity in the study of the equatorial hemisphere is essentially this magnetic declination. Since the electrodynamic processes are controlled by field-aligned, magnetic field-aligned conductivity effects, and this slope is essentially changes. So it's not only the change where the magnetic equator gets farther south has changed significantly, but is also the declination has changed over the last 50 years. I should point out, in the beginning of the 20th century, the magnetic equator was here. So essentially, there's a lot of very interesting, unique phenomena in the equatorial hemisphere. I'm going to concentrate in three important ones: the equatorial electrojet and their plasma instabilities, and I'll just touch on this one: the Appleton anomaly, and plasma depletions, enhancements, blobs, and spread F. Spread F essentially a lot of times used as a generic name for depletions and enhancements, and blobs are essentially a product. Consequence of these enhancements. So again, these phenomena are longitude, latitude, season, solar cycle, and magnetic activity dependent. So this is essentially comes, I think, from a study from the JAMP satellite, and introduces you the equatorial electrojet. So in the equatorial electrojet, at low altitudes, at about 90 kilometers, 95 kilometers, we have heavy collision, medium, so neither the ions nor the electrons move. At high altitudes, the collisions decrease dramatically, so electrons and ions cross B drift. So in this region, from about 90 to 110, 115 kilometers, you have essentially an ideal scenario where the electrons can cross B drift, setting up polarization fields here, and this polarization through a Hall effect generates a vertical field which drives a very strong current here. This current is confined to about 5 to 7 degrees of the magnetic equator. And actually what is interesting, even the focus of the magnetic equator can have changes of 1/3 or 1/4 of a degree on a day-to-day basis. So as a result of this, you have a very strong current. You have typical electron drift velocities here of about 500 meters, up to 500 meters per second, and a very strong current. So what makes the equatorial electrojet also very interesting medium is essentially the most turbulent medium in the Earth's upper hemisphere. You have plasma instabilities essentially all the time. These are characterized by so-called two-stream or Fale-Bunemann instabilities and the gradient drift instabilities. They have been studied in great detail. A lot of progress have been made on this, including the nonlinear simulations by Mears Oppenheim. So the next phenomena which I'll focus on is the Appleton anomaly. Appleton anomaly is so actually Appleton is a Nobel Prize winner, probably is the only ionospheric upper atmospheric work which at low latitude not. So the Appleton anomaly results from the fact that, as I'll show during the day, the plasma drift at the equator, the E cross B plasma drift. Whenever I talk about plasma drift, I'll be referring to E cross B motions. The plasma drift at the equator is upward during the day and transport the ionization to higher altitudes. Then eventually diffusion and gradient effects push this ionization to the sides at magnetic latitudes about 15 degrees, creating these two peaks, which are called the Appleton peaks, or ionization crest. Now, this is under condition of a very weak meridional field. If you have a meridional field, for example, from the summer to winter, then essentially this crest is pushed up, and this one is pushed down, creating essentially a very noticeable seasonal asymmetry. Another signature of the equatorial, of the Apoto anomaly is essentially the so-called Aurora Arcs. I mean, these regions of enhanced ionization, which persist way into the night, especially under high solar flux conditions, essentially causing very noticeable optical signatures, which essentially has been studied in detail. And one feature which I want to highlight here, which is already shown, there's a lot of incredible amount of longitudinal structure in all the processes in the equatorial hemisphere. Now, the next fundamentally important process at high latitude is essentially the equatorial spread F. And the basic idea of the equatorial spread F is very simple. This is essentially a very simple form of the Rayleigh terrain instability. Around sunset, when the lower part of the ionosphere essentially recombines and disappears, there are sharp gradients in the bottom side of the ionosphere, and this is an ideal medium for the so-called Rayleigh-Taylor instability. So in this medium, you consider you have very low plasma here, higher plasma here. So any little perturbation on this medium under the effect of the G cross B drift will set up polarization fields here, which will push the regions of higher density downward, the depletions, the smaller densities downward, and this depletion is going to move very rapidly to higher altitudes. Actually, so this is essentially what gives rise to the so-called ionospheric plasma depletions. One example is here, illustrated with data from SWARM. I should point out that these plasma depletions are associated with very large upward velocities and westward velocities. Very simple curl-free electric field condition. They can have very deep getting down to, so this is around, this was around 483 kilometers altitude, very deep depletions in the equatorial ionosphere here. And as I mentioned, these depletions are associated with large upward velocity. The largest upward velocity associated with the depletion, these actually a lot of these are supersonic. The highest have been measured by the Japanese Akebono satellite of 4 kilometers per second. So now another signature of this equatorial spread F or plasma depletions can be seen in optical measurements. These are really fundamentally important because affect a lot of systems. I should point out that the late Brazilian soybean king, which passed away about 10 days ago, was aware how plasma depletions affect his planting of his soybean fields. Some of them are as large as the state of New Hampshire. So the bottom line, you can imagine, and the other thing why this is fundamentally important here, that FAA have gone down to Brazil and determined that GPS-controlled altitudes can be in error by as much as 100 meters per second under these conditions. I should point out there are the 3 most busy airports in Latin America, 2 of them at least, Sao Paulo, Rio, are located in this region. This is a radius of, this diameter is 1,000 kilometers. I should point out these depletions originate at the equator and is essentially mapped along the magnetic field lines to much higher latitudes. So, so now equatorial spread F has a very impressive characteristic, covering a huge range of scale sizes, go hundreds of kilometers as in some of these depletions, and down to centimeters, almost the scale size of the ion Debye length. I mean, this is a signature of the equatorial plasma depletion measured with a 50 megahertz Hikamarka radar with samples backscattered from 3-meter waves. This is an experiment done by Mike Kelly. And this quasi-periodic structure, as well as the depletions shown earlier, suggest that some sort of seeding or modification associated with graduates. We can see the incredible amount of complexity on this structure. Some of them are sucked up all the way from the equatorial edge jet. This is essentially the equatorial edge jet here. You can examine this even in more detail. You use different techniques. And here we again see this periodic structure. This is essentially an interferometric picture obtained by TAFE HISO, where you can see this. So this is essentially the whole radar beam of the Hikamarka radar, and you can see these structures crossing this beam, measuring their zonal velocities, their vertical velocities. I should point out that these structures are tens of dB stronger than thermal fluctuations of the plasma. So when you have these structures in these regions, you cannot do incoherent scatter. Oops. Okay, so what all these three themes essentially are related by the fact that they are strongly affected by ionospheric plasma drifts and electric fields. So I'll focus on how these vary and what are the challenges we face when you try to study them. So the bottom line is they generating all sorts of structures. They are a result of essentially of the dynamo action of E region and F region winds, and driven by solar tides, lunar tides, and also affected by gravity waves, planetary waves, from scales from tens of meters to about a month. So they have been studied basically with, in terms of radar measurements, with observations from Micromarca, Peru, India, and also inferred from magnetic field measurements in Peru in a number of places. There's also the latitudinal variations and some of the longitudinal as well. Some of the latitudinal variation has been examined with a bunch of satellites, starting with the very successful AEE satellite mission in the 70s. So this is essentially one of my, I'll show you two of my favorite pictures of Micromarca. This actually is an old picture taken during the Condor rocket campaign, which was led by Mike Kelly. It essentially shows the global view of the Micromarca landscape before a number of different instruments have been placed. But essentially, this is my favorite one. Give you a full majestic view of this array here. I started using this array in 1972, so I'm quite fond of it. Anyway, so what I should point out, this is an impressive instrument. I mean, it's the most accurate measurement of electric field in space. The accuracy of this is 40 microvolts per meter with an integration time of 1 minute. So we can do really very, very accurate electric field measurement. This is fundamentally important because the electric fields at the equator are very small, of the order of 0.5 millivolt per meter, but essentially they control a lot. This very small electric field essentially play a very important role. I mean, in terms of electric fields at high latitude, they are really very, very small, but even these small electric fields are really fundamentally essential at low latitudes. So essentially, these illustrate two of the basic processes for measuring plasma drifts or E cross B motion in the equatorial ionosphere of Micromarca. So one is the incoherent scatter technique, where you put the 4 megawatt power of this radar into operation in different modes, and this illustrates the kind of data which you measure in this case. These drifts are largely height independent during the day. This is a fundamentally important parameter in the equatorial ionosphere called the preverse enhancement, and the drifts are downward at night. Now, a much easier operation of Micromarca can be carried out without in essentially unattended mode, using essentially transmitters with much lower power, about 20 kilowatts, essentially by observing backscatter from coherent echoes in the 150 kilometer region. Erhan Kudeki has shown, and Ron Woodman, Koki Chow later, that the plasma drift from this region mirrors very closely what happens at higher altitudes, even though there's some little variation. So this is a typical measurement of the velocity in this region. And there's very little variation as a function of height, as you can see by their color. Now, the equatorial measurements have started in 1968 when Ron Woodman and Thor Hagfors, the former director of the observatory, developed a very nice technique for measuring velocities very accurately. And when you point this accuracy results from the fact that the spectrum of the incoherent scatter echoes becomes very narrow in the equatorial region if you point the radar perpendicular to the geomagnetic field lines. And using a number of measurements, we have developed an equatorial plasma drift model for different seasons, solar flux values. And this gives you the idea of the quiet time variability here. using more recent measurements. So the bottom line, during the day, the plasma drifts about 20 meters per second during the day, and at night, with a solar flux increase in pre-reversal enhancement here. And they have significant seasonal variation. Now, the zonal drifts are essentially very little less with solar flux, and season they are westward at night with values about 50 meters per second and larger values at nighttime, which leads to a super rotation of the equatorial ionosphere. Now, one fundamentally important point which has been recognized to some extent by Rayleigh in 1974 with a work when he was still in England, is the fact that actually, even though these plasma drifts vary very little with altitude, this altitudinal variation of the drifts essentially is essentially a consequence of the curl-free nature of the electric field. But to a very large extent, all 95% of the work of the Equatorial Hemisphere has assumed that these values, which were measured between about 250 and 600, 700 kilometers, are representative of the Equatorial Hemisphere altitudes. Now, more recent measurements and studies show that actually, right around sunset, this is not a very good assumption. This is essentially results of a study which we carried out using a very clever scheme of radar pulses devised by Reinhard Kudecki, long pulse, shorter pulses interleaved, which allow to initially extend the measurements for the first time up to about 2,000 kilometers and examine this altitudinal variation in more detail, particularly around sunset, when Ron Woodman and his initial work has already suggested that things might not be much constant with altitude. And this is some of these plots here. So in the afternoon, things vary very little of altitude, and this is essentially typical of daytime conditions. Now when you get around this very important peak, the so-called pre-reversal enhancement, now you can have, in this data here, you have a dramatic variation of the plasma drift as a function of height. So the assumption that this value is constant with height using the value between 300 and 600 kilometers essentially gives you very large errors, a number of parameters, including essentially the latitudinal distribution of the Appleton anomaly, which is controlled by these higher altitude drifts. So this, I should point out, this is essentially the climatological value which actually has been used. Later, after a couple of hours after sunset, the altitudinal variation is starting to moderate again. Now, another fundamentally important characteristic of the equatorial hemisphere around dusk is the so-called equatorial vortex, which was essentially emphasized and examined very nicely by Reinhard Kudecki using a really a new way of analyzing the incoherent scatter radar measurements using a very clever technique. So this data essentially shows that around sunset, there is essentially a vortex here where around sunset, the drifts are upward and westward at lower altitudes and eastward and down at high altitudes. And it is this vortex which is essentially provide essentially ground for a very important process in terms of seeding equatorial spread F, in addition to probably with gravity waves. This is essentially the region where the plasma drift is driven westward and the winds are still driven eastward. So this gives rise to the so-called collisional shear instability, which was developed by Reinhard Kudecki and David Heisel. So this provides, for example, the seeding necessary for the Rayleigh-Taylor growth rate, which in the absence of significant initial perturbation is just too slow for explaining the observations. Now we have examined this shear in a little more detail. Here, using very detailed measurements. And here again, we illustrate the variation, the evolution of the altitudinal profiles of the vertical plasma drift around sunset. This is the corresponding zonal drift velocity. In the afternoon, the zonal drift velocity at these two altitudes varies exactly the same way. So if you apply the curl-free condition in a very simple fashion, you see that it requires that the plasma drift decreases with altitude. If you get closer to the time where the E region has disappeared, essentially, then the high altitude drift still continue to increase with altitude and leading to a decrease of the vertical plasma drifts with height, but the lower altitude drifts turn westward, and we essentially require that the bottom side of the ionosphere essentially move with a slow upward velocity. So this is essentially has a significant effect on the altitudinal distribution of the plasma around sunset. And at high altitudes, essentially the drifts again start to become constant with altitude. So the bottom line, this was under very low solar flux condition. In this case, the measurements could not be extended with significant accuracy to higher altitudes. Another really major challenge for understanding spread F and equatorial plasma depletions is that these altitudinal variations are extremely variable from day to day and as a function of height. This is two collection of data. One is under solar max condition, so time is increasing this way. You can see you change the altitudinal profile for very weakly height varying to the essentially the pattern of increasing velocity on the bottom side, decreasing and then becoming constant. So, and then you continue this way, and there's no data here because of the occurrence already of equatorial spread F, which starts right around this region. So this is another example. You can see you have a large number of very different altitudinal patterns on these drifts, and of course this leads to very different distribution of the plasma 1 or 2 hours later. I should point out that actually what happens in the equatorial plasma drifts 2 hours early is what determines the shape of the Apoto anomaly, because it takes about 2 hours for the plasma to be transported and up in altitude and essentially diffuse along the magnetic field lines. Now, so this already illustrates the very large variability which you see in the equatorial ionosphere. And actually, this is not restricted to the daytime. This is an example of the day-to-day variability of the equatorial plasma drifts right at noon. And the fundamentally important feature of this data is the fact this variability is remarkably stronger at lower solar flux condition, which means the barrier between the lower and upper thermosphere is essentially very porous under low solar flux condition. All sorts of planetary waves, gravity waves, and so on are able to produce electrodynamic effects with much higher efficiency under low solar flux conditions. So the bottom line is that over the last decade or so, when solar flux conditions were quite modest, I mean, the predictability of this phenomenon was essentially significantly more difficult than over past years. Now, one other very important phenomenon which has been recently studied in great detail and which illustrates the incredible amount of coupling which occurs in the Earth's ionosphere is the so-called southern stratospheric warming events. Southern stratospheric warming events are associated with rise in the temperature in the stratosphere about 30 kilometers in the polar regions, and the essentially turning of the new zonal wind to westward direction. The black curve is essentially the 30-minute averages. The red ones are the values of the temperature during 2010. And this causes essentially very large perturbations of the equatorial plasma drift. These are the values obtained by removing the quiet time climatological values. You see very large perturbations in this case with periods of about 14 days. Some of these are associated with enhanced lunar semidiurnal tides. There are a bunch of other effects which take place, and there's a lot of very nice simulation being done along these lines using very sophisticated models. of course, as you change essentially the plasma transport at the equator, you modify dramatically the distribution of the apoto anomaly, because essentially the fountain effect varies significantly during this period. And this is a very nice study done using with TC measurements from Arecibo, from the American sector by Larissa Goncharenko and Koki Chow. Now, to be able to examine how these processes change, if you get away from the American sector, we have to get into satellite measurements. There's a bunch of measurements from India, a few from Asia, now, luckily, fortunately, much more from Africa. But essentially, the satellites were essentially our main tool for examining how these processes, which vary as you move in to different longitudes. And there's a lot, as I mentioned earlier, there's a lot of very effective satellite probes which have been studied on this. So these are the two ones which are making measurements right now. One is the CNAV satellite measurements. I just heard this morning that this is being renamed a T-Rex since it's dying. And the so-called European Space Agency mission Swarm 3, which consists of 3 satellites. Actually, B and C now has been changed in altitude. So 2 side by side at 1 degree separation, temporal separation 1 degree, high inclination orbit, and the other one at 520 degrees. So this CNAV measurement and this very challenging and interesting region of the lower ionosphere, as it's decaying, is going to provide fundamentally important information on the polar vortex, on the equatorial vortex, velocity vortex, and its role on the generation of equatorial spread F, and a bunch of very interesting phenomena, since the lower part of the sunset ionosphere in particular has been very difficult to explore because of very low signal-noise ratios, which you get when using radar measurements. Also, the MSP has been also providing for a large number of years very, very useful complementary information with the measurements at low latitude. Now, the satellite measurements are already extensive enough to have an idea how this longitudinal variation takes place of the equatorial plasma drift. This is the measurements derived from 5 years of rockset data, which shows essentially a very, very strong structure, particularly during the day. This is so-called 4-wave structure, which is associated with so-called D3 waves, which Tim Fullerall emphasized very nicely in the tutorial last year. The zonal, and also you can see the very strong longitudinal variation of the pre-reversal enhancement here, which is strongest in the American sector, around the American sector in December solstice, and weakest in that sector in June solstice. This is the sole reason why equatorial spread F essentially was not observed during June solstice over Peru. The more recent measurements from CNAV also show that there's also very, very strong longitudinal dependence on the zonal plasma drift. And here again, you can see it is really the in the American sector, there's very large and strong longitudinal dependence around sunset. And this has to do with the fact of the change of magnetic declination as a function of latitude. Now, this illustrates how the electrodynamic processes taking place in the F region are mirrored by what happens in the region. So this is the result from Hermann Luhr of CHAMP satellite measurements from the equatorial electrojust, showing this so-called 4-wave structure, and these are the measurements from ROCSAT. And this is a plot which Tim Fullerall said he got from the web. Essentially shows lightning activity. I mean, this 4-wave structure has been explained in terms of convective storms taking place over essentially the continent. Very nice theory associated, which essentially these global measurements were essentially were able to show that are significantly correct in most of their aspects. Now, one fundamentally important equatorial spread F, as I mentioned, is the so-called pre-reversal enhancement of the vertical plasma drift around sunset. This plot shows the variation based on the rock set data. And what you see is the remarkably strong variation, especially during the solstice. And you notice here the anti-correlation of the variation during December solstice and June solstice. This is a pure result of the change in the declination and on the angle which the solar terminator makes with the magnetic field lines in this sector. This, I should point out, this is essentially basically the longitude where the magnetic field geometry changes its declination from positive to negative. During equinox, things are a little more uniform. As a result, this causes a dramatic variation, seasonal variation on the distribution of equatorial plasma depletions, which to a large extent are controlled by this vertical plasma drift. I mean, a lot of these studies have been done in terms of satellite measurements of these depletions. And this is a very nice study by a very extensive data set based on the MSP measurements at 840 kilometers near solar maximum. So this is essentially the magnetic field lines aligned with the terminator here, and which illustrates that during December solstice, we have a very strong occurrence of equatorial plasma depletions at the equator associated with the fact that there's very strong pre-reversal enhancement. Whereas in June solstice, there is essentially no plasma depletions at the equator, at least under quiet time conditions. This is also a very interesting region of the equatorial South American anomaly, where the magnetic field is the weakest from anywhere in the world. So these measurements are really restricted to 840 kilometers. So one fundamental thing to keep in mind is that different probes will see essentially different statistics as a result of the different signature of the different processes. These are simultaneous, almost simultaneous and collocated measurements from swarm A, B, and C when all the three satellites were at the same altitude, about 502 kilometers before they kicked one of them a little bit down in altitude and the other one a little bit up. And these measurements from the DMS pole, so 500 kilometers and 840 kilometers. DMSP during this whole period essentially see no depletions, even though the swarm at lower altitudes saw even very, very deep depletion. I should point out that these lines correspond to map to the apex altitude of the MSP. So you're going to have, based on the MSP, you think that essentially there's no sunset depletions during this low solar flux, moderately low solar flux period, and yet swarm saw all this place. And the other important features here is the fact that these depletions are incredibly dynamic. The three swarm satellites at this time were separated by only 6 minutes apart and at the same altitude. So it's incredible large dynamic range on these variations. So I'll spend a few more minutes now on the response of the Equatorial Hemisphere to geomagnetic activity. This is a topic very, very dear to me and is an incredibly interesting topic. And I should point out that actually we understand this stuff much better than the variation at quiet times, because we have all these complex processes at quiet time have an incredibly large range of time scales, and essentially magnetic activities, especially under strong conditions, are much more easily identifiable by removing the climatological values. The basic processes are actually quite well understood, and actually one is essentially the so-called prompt penetration of equatorial of electric fields from the auroral zone down to the equator, and this so-called disturbance dynamo. Both of these theories actually were developed in the 1980s. Prompt penetration electric field theory, morphology, getting down all the way down the equator was developed by Dick Wolf in the early 1980s, and the disturbance dynamo theory, very successful still, was developed by Michel Blanc and Art Richmond in in 1980. So the bottom line, the basic process is the following. If you have a rapid change in the high latitude convection, then the region 2 field-aligned current is unable to shield the low latitude from the high latitude. So during a period of tens of minutes to 1 or 2 hours, essentially the changes in the high latitude convection get down all the way to the equatorial ionosphere. And this takes place by essentially a transverse magnetic mode propagating the Earth ionosphere waveguide. So this lasts from minutes in general until the region 2 field, the ring current and the region 2 field-aligned current can reconfigure itself. So this causes eastward, so increase in convection causes eastward electric fields during the day and westward at night. So this is signature of increase in convection, increase on convection, decrease, increase, decrease, and so on. Here, equatorial ionosphere kicked in spread F, which actually is a consequence of a lot of these processes. And then on this period, essentially, things got essentially back to normal conditions. But surprisingly, essentially, 1 day later, a very noticeable and longer-lasting perturbation take place, and this is essentially what characterized the disturbance dynamo. Essentially, what happens here when you dump a lot of energy at high latitude, you essentially completely mess up the quiet time wind pattern. And essentially this energy is essentially going to move down to lower latitude and completely change the transport processes out there. So the upshot is that for you to understand what happened in the transport process in the equatorial hemisphere at one time, you essentially have to go back about 30 hours in terms of the magnetic activity. One impressive feature of this is that the prompt penetration electric fields are instantaneous at all latitudes. This is actually a figure from Cesar Gonzalez et al., actually inspired by Mike Kelly. So this is the variation of the horizontal magnetic field at Addis Ababa, Ethiopia, and essentially these perturbations are a result of prompt penetration electric field. And here, these are positive is correspond to eastward perturbation here, positive correspond to westward here. And Mike Kelly have reversed these figures to show much more closely how correlated and essentially instantaneous are these perturbations associated with prompt penetration electric field all over the globe at the same time. Now, the other one, as I mentioned, is essentially the disturbance dynamo place, which is illustrated here. In this case, during June 11, there was essentially a large amount of magnetic activity, which rapidly decreased here, and things actually shortly after became quite quiet. So in the equatorial hemisphere, unfortunately, during this third period, we have no measurements. And here, shortly after, during its decreasing phase, where the process we're going to talk about there's a lot of very interesting processes, including magnetic reconfiguration and so-called fossil winds take place. But the more important ones here is the one which took place essentially 1 day after this large auroral perturbation, and is essentially this smooth and systematic departure of the equatorial upward drift to much lower values. This is what characterizes essentially equatorial disturbance dynamo. So longer lasting periods which take place in response to large energy deposition, mostly through Joule heating into the high latitude ionosphere. So again, as I mentioned, the Blank-Richman theory essentially has been very successful in explaining most of the feature of this process. Satellite measurements have provided now new information how to look in this in terms of seasonal variations and longitudinal variations. Now, this is essentially the patterns which you see associated with sudden increase in high latitude in the auroral currents. So this is the so-called undershielding conditions. What this data shows is that this response depends very strongly on seasons, particularly at night, when the penetration electric fields have larger amplitude. And basically what happens here is that prompt penetration effects increase with decreasing conductivity and decrease with decreasing conductivity. There's better shielding to going down to higher latitudes under higher solar flux conditions. And I should point out that the response is strongest in June solstice than in December solstice. And this is associated with the well-known effect which was pointed out extensively by Henry Richbeth and also mentioned by Mike Mendil earlier. And all over the globe, the ionospheric densities are lowest during June solstice and highest during December solstice. Now, if you have a sudden decrease in convection, what you're going to have essentially is these reverse patterns. So you're going to have downward velocities during the day and upward velocities at night. And these upward velocities at night associated with prompt penetration are going to be able to generate equatorial spread F in the post-midnight period. Now, the disturbance dynamo effects are difficult to extract from satellite measurement. I mean, they are small during the day, consistent with the prediction of the Blank and Richmond model. And essentially, they have the opposite, basically the opposite variations in terms of density here. So they are weakest during June solstice and largest during December solstice. Now, if you have a storm with increasing, decreasing convection lasting for several days, you have a mixture of all these things taking place at the same time. As I mentioned, these disturbance dynamo effects actually can last up to 30 hours after large injection of high latitude of energy into the high latitude ionosphere. There's a lot of very even more challenging questions right when there's significant decreases on the high latitude convection, because then you have effects associated with magnetic ray configuration. We have effects associated with so-called fossil winds, which makes these pictures a little more complex. Now, as I mentioned, one fundamental aspect of these perturbation electric fields, they cause dramatic changes in the equatorial ionosphere. So this was the largest prompt penetration electric field detected at Icamaarca so far. So the typical values during the day are about 20 meters per second, and these went up to about 120 meters per second. So this very large upward velocity essentially kicked up the plasma, essentially completed to very, very high altitudes, actually above the height range sampled by the radar. This is the radar signal to noise ratio. This is proportional to the electron density. And when this perturbation electric field decayed here, essentially you have a new ionization layer coming down here. This is so-called F3 layer, which has been studied in connection with this event. So the bottom line is that now another fundamental aspect which happens under these conditions is that you have a remarkable change in the distribution of the ionization as a function of latitude. And of course, this is the response in the equatorial ionosphere over Peru. Over Indian sector, under these conditions, there would have been a remarkable decrease on the height of the layer. So the whole layer over the India in this period would have been compressed to very, very low altitude, and as a result would recombine also to small values. So now these very large prompt penetration storm time electric fields cause very dramatic change over a huge range of latitudes. These are very nice measurements published by Shanti and Sunanda Basu in 1980 in response to the so-called Bastille Day, the storm of July 15, 16, 2000. These are the DMSP passes on the magnetic sector. And as these very strong pump penetration, and these satellites are in the near the dusk sector, so where prompt penetration electric field, as I illustrated, cause an increase of the upward velocities at the equator, and very strong uplift of the plasma, causing essentially the plasma to disappear at the equatorial region and to be shoved all to much higher latitudes than the traditional latitudes of the Apoto anomaly. At the same time, upward velocities are favorable to lead to very large values of the Rayleigh-Taylor growth rate, and then you start seeing a very large number of plasma depletions associated with these things. as I mentioned, since the polarity of this prompt penetration electric field is different during the day and night, in the post-midnight sectors, during this case, there was essentially no spread F because there would be very large downward velocities, which essentially are responsible for killing the generation of these waves. Now over the last few years, having a large number of very, very useful, very nice probes being developed all around the world, which essentially will provide much more useful information of how longitudinal effects modulate this ionospheric, this important ionospheric phenomenon. This is a slide which I got from Marco Milla, which illustrates some of the new instrumentations which is being placed around the Hicamarca radio observatory. This includes the EMISER system, which is ideally suited for making equatorial spread F and equatorial electric jet measurement at the same time at several different angles, and a number of very important probes, including the air glow measurements and the Fabry-Perot, which provide information on the neutral parameters, which are not really discussed much here. So this is essentially a very nice slew of instrumentation which can provide significant more information on this complex phenomenon. Of course, together goes with the important challenge. Once you get all this information, it is crucial now to integrate these measurements in a consistent fashion, and that's a challenge in more ways than one, including in terms of funding. Okay, so we generate a lot of data. Sometimes it's not easy to be able to have resources to examine all this information in as much details as it deserves. Now, as I mentioned, so there's a similar set of diverse instrumentation in Brazil, including, I should point out, very expensive GPS network, because, by the way, GPS in Brazil was significantly expanded in its numbers because the impact on deep oil extraction of the Brazilian coast. I don't know how that's going now that the country is in more financial difficulties, and over Africa. So you should have much more important information on these processes. However, even as much as this large cluster of information is important, it is important also to keep in mind that satellite missions, small ones like Carina, or some of the ones larger like ICON, are really fundamental because they provide focused on some key phenomena at essentially with a large range of time scales and different longitudes. And actually one which I want to emphasize, which I think regrettably hasn't happened for a long time, is essentially this dipping satellite. I find it remarkable that in 1974 we were capable of measuring deep satellite measurements at low latitude, getting down to 150 kilometers, which is essentially a fundamentally important region which for a long time has been called the ionosphere. And that these measurements hasn't been made since this long time, even though technology has dramatically changed. And these missions, similar missions, would be really very useful, not only at the Equatorial region, also in the Aurora region. And by the way, this is a dream of Rob Pfaff, which I think its big importance essentially deserves to be considered seriously. Okay, in summary, I hope I give you an idea of essentially the Equatorial Hemisphere as an incredibly rich medium, which reflects the incredible degree of coupling to higher latitudes, low latitudes, response to just about any significant perturbation, including winds over the Andes or tsunamis or lightning. I should point out that, for example, lightning can trigger spread F, and that has been established by Mike Kelly and Farley in a nice paper about 20 years ago. Incredible large range of scale sizes, temporal scales, and at a given tournament, a lot of these phenomena take place at the same time. So it's always very challenging to be able to fully understand what each one of these what role each one of these phenomena is playing. So I focused on transport processes, and is basically a little bit on the effects in terms of plasma instability. I should point out that very nice modeling work has been done in terms of the electrodynamics and effects. We've examined the effects of tides, planetary waves, and so on. I have not focused on this stuff, but I think these experimental studies provides very important information for the validation and testing of these models. The most challenging part of the Equatorial Hemisphere is essentially is this evening sector, where there's a very complex variation, very complex temporal and a very large altitudinal variation with which is very different in different areas of the globe. This is essentially, in spite of all the very successful models, I think this is the region, this is the area where knowledge is significant, needs to be significantly improved. This is where future missions, ICON, CARINA, and complementary modeling can really help a lot. So and this goes along the possible seed mechanisms of equatorial spread F, such as gravity waves, and without doubt the examination in more detail of the collisional shear instability, which has only been examined now in detail with rocket measurement and some of the simulations by Hakudeki and Dan Hai. So now actually in a sense is surprising, but actually we understand much better at least the basic characteristics of the electrodynamic response at low latitudes to geomagnetic activity. Largely because the quiet time effects are all comparable. It's really very difficult to separate them unless you have a lot of data and patience. But still, even here, there are really some fundamental important parameters we don't know. We don't know, for example, the most important ones is that what does IMF-BY does? Not only in terms of prompt penetration electric field, but also in terms of disturbance dynamo. After all, in the two hemispheres, in the northern and southern hemisphere, the energy is deposited in different longitudes. How does this energy gets down, and what are these effects when it reaches the equatorial region? As I mentioned, general circulation model like the Rice convection model, the convection models like the Rice convection model, general circulation model, equatorial spread F theories by Dave Heiso, John Retterer, Joe Huba, and others have explained a lot of features, but I mean there's still a fair amount of keep information which is necessary to go to this to the present stage of to providing at least more reliable predictability. And some of them deal with the fact that the fundamental importance of the pre-variation enhancement and what are the parameters which determine the variation of the pre-reversal enhancement. Okay, what happens in the afternoon, in the daytime and an afternoon sector, which is going to precondition the pre-reversal enhancement to have large enough values to trigger equatorial spread F? We have absolutely no idea. Okay, so the bottom line is that I hope that I have shown you that there's a lot of a lot of progress has been made in the study of the Equatorial Hemisphere, but there's a lot of very exciting and interesting and challenging topics left for the near midterm future. Thank you very much.